clear engagement. So thank you, John, and it's 1 + 20. 1 hour + 20 minutes. Yeah.
Thank you. And thanks again for the invitation. And the connection between the two topics, I guess, is that we'll argue that YbRh2Si2 is a candidate triplet superconductor, and hence potentially a topological superconductor, and those in crystalline form are in relatively short supply. So let me acknowledge then the people who did the work. So Lev Levitin has been really driving the transport measurements, and Jan Knapp, towards the end of his thesis, has done some amazing heat capacity measurements with a lot of support from Lev. This is a collaboration with the Max Planck Institute in Dresden, led by Manuel Brando at that end. Engagement with Christoph Geibel has been very, very important, and Kent Shearer has made some marvelous FIB machine samples for us. The crystals come from Cornelius Krellner Group in Frankfurt, and we have this long-standing collaboration with PTB in Berlin, where we get these high-quality two-stage squids from. And the work has been primarily supported by the European microkelvin platform, and I'll have a couple of slides about that entity, and it's in an environment of some funding from YbRh2Si, or though actually there's no funding for this project. So I'm going to give a brief introduction to YRS, then go over the proposal of superconductivity in the first paper on this subject by Schubert et al., and a limited discussion of the proposed underlying mechanism from YbRh2Si. Then I'm going to talk about the measurements that we've made in reverse historical order, essentially, because I think the heat capacity study is relatively clear, and it provides an important context for the transport measurements. And there I'll show data of what we'll refer to as an electro-nuclear phase transition, then spend some time talking about the transport measurements at ultra-low temperatures, which also involve new methods for working in this extreme temperature regime. And so we have data on single crystals, samples, effectively wires of YRS machined by focused ion beam techniques. And we also have results on isotopically enriched samples. Have some discussion about the possibility of spin triplet pairing. So to resonate with Pierre's introduction, then the question is there potential new physics which is triggered by the strong coupling of nuclear spins to electronic magnetism and superconductivity in this material? And the other thing that this relates to, I guess, but I won't speak very much about it, is the strange metal idea, and whether there are limits to quantum criticality in systems with strong hyperfine coupling, and that's been discussed in this theoretical paper. So heavy fermion is a tetragonal system. The Fermi surface hasn't been measured, but it's rather complicated, consisting of various pieces. Here's this jungle gym piece. The effective mass varies hugely over the Fermi surface. So the blue regions are the regions with low Fermi velocity, hence high effective mass. And the relevance of this to the observed properties of YbRh2Si is, as far as I can make out, being new to the field, not discussed an awful lot in the literature, maybe because this object is a very complicated object. So important characteristics of this material is that the electronic magnetism is highly anisotropic. remarkably, it shows a sharp ESR resonance in the heavy fermion regime. That's attributable to the presence of ferromagnetic spin fluctuations, according to a theory by YbRh2Si and Abrahams. The G factor measured by ESR is highly anisotropic, so it's 3.6 for the field along the c-axis and 0.17 along the c-axis, so 3.6 perpendicular to the c-axis. I misspoke, sorry for that. And this anisotropy reflects the highly anisotropic nature of the pseudo-spin ground state doublet of the terbium moments in the crystalline electric field. Then there's all this work which indicates that the system exhibits both antiferromagnetic and ferromagnetic spin fluctuations. The presence of ferromagnetic spin fluctuations in this system is somewhat undersold, I would say. So that comes from neutron scattering. It also comes from NMR and measurements of the magnetization. And the other key characteristic that distinguishes it from cerium-based heavy fermion materials is that there are these species with nuclear spin that have an extremely strong hyperfine coupling of 102 Tesla per mu b. So mu b would be the effective moment on the effective local electronic moment arising from the 4f electrons. So you're probably all familiar with the field-tuned quantum criticality in this system. This is the field being varied in plane. So in low magnetic fields, antiferromagnetic order develops below about 70 millikelvin. And according to mu-SR measurements, the ordered moment, the static ordered moment, is extremely small. It's only 0.002 mu b. Then there's another important measurement, which is also hasn't received an awful lot of attention, I think, which is if you tune the field in plane, what happens? You develop an in-plane moment that grows linearly with in-plane field to a value of about 0.1 mu b at the quantum critical field. So over here, you go into a Fermi liquid state. The moment here is 0.1 mu b. If you come measure resistivity going down in this direction, it has this linear T dependence and then goes over to a Fermi liquid dependence below the Néel point. So although we know the size of the moment, the nature of this order is not established. We don't know the direction of the moment. So Brando and colleagues did a lot of work on doping with cobalt the material in order to boost the ordering temperatures. And you see, and it's referred to in this paper, a complex phase diagram. One insight on the pure material. So this axis here is the cobalt doping. So the claim is that the moments are oriented along the C axis, which is the hard axis, the axis with the smallest G factor. And I believe that Frank and Andrew have a theory of that. So now to superconductivity then. So this was the 2016 result. So for me, this and actually only this is the evidence for superconductivity in this material. So from this paper. In very low magnetic fields, you see here we've got a field of 12 microtesla. There is evidence of strong diamagnetic screening. There is hysteresis in that. And there are also measurements of AC susceptibility, which show diamagnetic screening. And there's this interesting precursor feature, which is going to be relevant later on at a temperature T sub B. And this notation for characteristic temperatures, I'm going to be using throughout the talk to label features that we also see. The other very interesting observation by these guys was they measured the heat capacity at an in-plane field of 2.4 millitesla. So they had to subtract what they believed to be the quadrupolar heat capacity from the data. So this is the what's left after you've done that. And what you see is this anomalous feature in the heat capacity. Looking at the magnetization data, then there's a peak in magnetization around 2 millikelvin, and the paper contains interpretation of these various features around the peak. The locus of that peak as a function of magnetic field is these red points here, and so the interpretation then was that below these temperatures you have both antiferromagnetism and superconductivity, and the interpretation that was offered was that at this temperature what happens is you get hybrid nuclear electronic order, which leads to suppression. You can see this here then at this temperature. Here's the antiferromagnetic order parameter that's developing below the Néel temperature, 70 millikelvin. And then down here at T sub hybrid, then there's another transition in which the antiferromagnetism weakens and the superconductivity appears. This was the hypothesis of that work. And so the narrative around it then was that, okay, over here you've got a quantum critical point. Somehow or other that quantum critical point has been shifted to low magnetic fields by this destruction of the antiferromagnetic order by this hybridization in interaction. And this is a hypothesis that we wanted to test in our own experiments. So our own experiments involve this collaboration with Dresden and are facilitated by the European microkelvin platform, which was funded from January 2019, although our collaboration with them started before that. So it's a network of laboratories which have microkelvin platforms across Europe. And provides transnational access, and we are one of 8 access giving facilities. These are our facilities. So we have 4 nuclear demagnetization cryostats, one with a high field low T capability that's been used for example, quantum oscillations experiments with the high field lab in Nijmegen. And we also have a prototype of a high performance cryogen free microkelvin platform with a large amount of real estate for mounting experiments. And the ability then to write a 2-page proposal to generate money to do an experiment with a collaborator in Europe has been a huge contributor to the efficacy of what we've been able to do. So now I want to show you a piece of data which when I walked into the lab and Jan Knapp showed me this, I almost fell over. So this is the heat capacity as a function of temperature measured by this new technique from about 100 millikelvin to about 100 microkelvin. And this is a challenge to do this. And what you see in this data is the sharp Néel transition that we've been referring to, and a very sharp low temperature anomaly. So this is the version of the original anomaly seen in the Schubert experiment, but done in zero magnetic field. And just as a spoiler then, in the transport measurements, which are going to come to later on in the talk, what we also see is superconductivity develops at much higher temperatures, typically 6 millikelvin in these samples. but because of the way that we do the transport measurements, so we measure the real and the imaginary parts of the conductivity. So we're sensitive to the, for example, the kinetic inductance of the sample, and that shows a small signature here. And the signature is tiny, it's some tens of nanoohms, but we can detect it. And so what this is indicating is it's a change in the superconducting state above and below the transport signature, which pretty well, these measurements are done on 2 different cryostats, but the temperature scales are extremely well aligned because they're based on noise thermometry. It indicates that the superconductivity is happening at the same time as this nuclear magnetic driven transition. And so that raises the possibility of, and it's only a possibility at this stage, we can discuss it later, of intertwined order. So I now want to spend a little bit of time then on the details of the heat capacity measurement. So we apply in-plane magnetic fields, and what happens is this sharp anomaly that we saw here at about 1.5 millikelvin shifts down in temperature and broadens. And I want to emphasize the fact that while at 0 magnetic field, where we had this sharp anomaly that coincided with the superconducting transition, at 21.1 millitesla, we see this broadened anomaly in the heat capacity, but at that field, the sample isn't superconducting. It's important to bear that piece of experimental information in mind. So this is primarily a theoretical audience, so I won't dwell on these slides, but we use fast noise thermometry. Noise thermometry has never been used for heat capacity measurements before. We're doing measurements on, and it has to be fast, as you'll see in a minute. We're doing measurements on a tiny sample, 20 milligrams. It's thermalized through an aluminium wire, which acts as a superconducting heat switch, which has a critical field of 10 millitesla. So we can take data in a variety of ways that are indicated here. So this is temperature as a function of time, starting off at 175 microkelvin. There's the warm up of the sample in a heat leak of 31 femtowatts. This tiny heat leak is achieved by extremely good shielding and screening of leads in the sample. And then we apply a small heat pulse. So that's effectively the adiabatic technique. And then there are other techniques that are used in different parts of the phase diagram. This heat capacity that we're measuring, we measure it from 0 millitesla up to 69 millitesla. So we measure it to beyond the in-plane quantum critical field. And before I show you the details of that, I just want to be clear about what the origin of it is. With all of this data, if we integrate the heat capacity, what we get to some pretty high degree of precision is the total nuclear spin entropy of 171 and 173 ytterbium. So it's clear that we're measuring the nuclear spins here. Let's look at that then. So we're using the nuclear, this is what we believe is happening. We're using the nuclear entropy as a window on the electronic magnetism. So the nuclear spins have a quadrupole interaction for 173, which has a quadrupole moment. And both species, 171 is spin a half, so no quadrupole moment, have got a Zeeman interaction with the hyperfine field. And the origin of the hyperfine field then is because we're in the so-called fast relaxation regime, the ytterbium nuclei are subject to the hyperfine field produced by the static part of the electronic moment. These are the energy levels for the 2 spin species, which were obtained for us by diagonalizing the Hamiltonian by Andrew Ho. So this data here in zero magnetic field, effectively, we can neglect this term here because the local moment is so small, and so we can fit the data above this transition to the heavy fermion contribution. So that's the gamma of the heavy fermion system, which agrees with the accepted value, and the magnitude of the quadrupole interaction, where we obtain a number that was significantly smaller than the accepted value. But on closer examination of the literature, there is no actual measurement of the quadrupole interaction under ambient conditions. This was an extrapolation from other data. So we have measured the quadrupole interaction in this system and its sign for the first time. And that's important in the analysis of the data, so we can fix the quadrupole interaction going forward. And then the parameter is going to be the hyperfine field experienced by these nuclear spins arising from the electronic moment. So the nuclear entropy then is, through that mechanism, the window on the electronic magnetism. Okay, so what we see in more detail then is over this field range, we see that we see this anomaly, and what we can do is we can fit the data at temperatures above the anomaly, and the fit parameter there is the hyperfine field, which determines the electronic moment given the accepted value of the hyperfine constant. At these larger magnetic fields, we see no anomaly, and we can fit the data over more or less the whole temperature range to determine this hyperfine field. And when we do that as a function of in-plane field, so that's the hyperfine field as a function of in-plane field, and here is the size of the electronic moment as inferred from that hyperfine field. What we find the red data. So we find this linear increase in the size of that moment, which is very similar to the linear increase that was previously observed by Brando in this paper. So that piece of physics is essential, that as you apply a field in plane, there's a growth of the in-plane moment on top of whatever antiferromagnetic order that you have. And then what happens is you have the anomaly, and clearly the fits above the anomaly can't account for the data below the anomaly. So there is a transition. And that transition involves the electronic moments in some way. So the question is, what is the nature of that transition? So now if we just look at the data at extremely low temperatures, we can't explain that data in terms of a uniform hyperfine field experienced by the nuclei, because they would give a too rapid roll-off in the heat capacity. What we have to do is we have to posit a modulated hyperfine field, such as would arise from a spin density wave, and then the as indicated here. So there's a modulated electronic moment. It's incommensurate with the lattice. And remember, this is a key thing. Who is that? Go away. Remember, and this is key, that we have 14% 171 ytterbium and 16% 173 ytterbium, and obviously they're randomly distributed across the ytterbium sites. So any modulation in the electronic moment, such as this, is going to give you a random modulation of the hyperfine field seen at those ytterbium sites. So the nuclear spins then are a diagnostic for spatially modulated electron spin density, which is appearing at temperatures less than TA. And just by fitting the low temperature data where it would be natural to assume that the amplitude of that modulation is no longer temperature dependent, we find that the amplitude is 0.093 μb, which is very similar to the 0.1 μb that you get at the quantum critical point induced by an external magnetic field. Remember, at the moment, we're in zero magnetic field. So now you would say to yourself, well, okay, if we have some, let me loosely call it a spin density wave order, you would say, well, okay, there's going to be some order parameter associated with that. So let's just write something of this form and fit the data. And what you can indeed do a pretty good fit to the data. That's the red line. We're again in zero magnetic field with a rather small value of the exponent, something that's in the ballpark of the exponent that you might have in an Ising type model. This exponent is not a mean field exponent. That would be, as I understand it, 0.5. So that indicates that there are strong critical point fluctuations at this temperature of 1.5 millikelvin. And that would imply a short coherence length then through the Ginzburg criterion. So you might ask yourself the question, you're claiming that this is a continuous phase transition. Why isn't it just a first order translation that's broadened in some way? So what we do is we warm through the transition at different rates, and we find that changing that rate by more than an order of magnitude, the data is the same, and the heat capacity derived from this continuous warm up agrees with the pulse data. And so we believe on experimental grounds that it's a continuous phase transition. And we also have theoretical grounds for believing that. So why does this transition happen? And so as experimentalists, then all that we're confident in doing is some thermodynamics. So what this data that I keep referring to, at 50 millikelvin, the growth of the in-plane moment as a function of magnetic field tells you, is when you integrate it, it tells you the energy cost to create an in-plane moment of about 0.1 μb here. And if you use this data to calculate that energy cost, it's only 2 millikelvin. That's a much smaller energy scale than the Néel temperature and energy scale. So this is very unlikely to be anything to do with canting of the pre-existing electronic order at the Néel point. There's some other fragility of the electronic, I like that word, fragility of the electronic magnetism in YrS, such as these tiny in-plane fields with energy scales of only 2 millikelvin can do something. So if such small magnetic fields can do something, then maybe the nuclear spins can also do something. And so what you do then is, or what we did then, is to write down a free energy of the following form. So this is the energy of the nuclear spins, which are experiencing a hyperfine field. So we're not considering anything to do with interactions between nuclear spins. They're just experiencing the hyperfine field due to the electronic magnetism. And the electronic magnetism has two origins. Then there's the in-plane moment that's induced by an applied magnetic field, and then there's the amplitude of this inverted commas spin density wave order that's appearing spontaneously below 1.5 millikelvin. And we assume that those two moments are orthogonal to one another. And I'm not going to go into details, and Jan Knapp is in the audience. I should have pointed him out before. So just to say that this simple experimentalist model captures a bunch of different physics. It captures the fact that the phase transition should be continuous. It captures the order of magnitude of Tc, that the transition should shift down in temperature and broaden with magnetic field. And it also predicts that this so-called spin density wave state will be destroyed by a critical field that's determined by the ratio of these two coefficients. Clearly, alpha is smaller than betas, so that the cost of forming spin density wave order is smaller than forming kind of paramagnetic order. Okay, so what of course this leaves a lot of things out. One of the things that it leaves out is that at low fields, this order that we're discussing may be intertwined with the superconducting order parameter, which I'm going to argue is spin triplet. Okay, so now on to transport. So we're measuring transport initially on single crystal samples, using a two-stage squid as a very sensitive current amplifier. And without going too much into the technical details, we can measure three things with this setup. We can measure the complex impedance of the sample. So the sample impedance is denoted by Z sub S. There are contacts made by bonding gold wires to the, aluminium wires to the sample. And this contact resistance then involves some region at that surface of the YbRh2Si silicon. So we can measure the contact resistance using that technique, and we can do it both of these with nano-ohm precision. And the other point I should have emphasized is that we're measuring the complex impedance, so we can look for inductive terms, which in the measurement, which I don't think is habitually done in transport measurements on superconductors. That tells us a lot. We can operate that in the normal state. We can operate this device as a noise thermometer. So this is resistive. There's Johnson-Nyquist noise. It's driving current through this input circuit of the squid. The squid is a current voltage amplifier. So using this as a noise thermometer then confirms the sample thermalization, and in early work actually confirmed that the loss of resistance, so the disappearance of Johnson-Nyquist noise, is associated with the turning off of the resistance at the superconducting transition. And if the sample is superconducting, then we can have a closed superconducting loop in which you would expect to see persistent currents. So we can see all of these things. So in the normal state then, so here's the heat capacity measurement. So there's the Néel transition. So above the Néel transition, we have this linear temperature dependence of the resistance, so-called strange metal behavior. And then at Tn, to very good precision, we go from linear to quadratic. That means then clearly that Fermi liquid state is formed at T less than Tn. So that when the superconductivity appears, it's appearing out of a Fermi liquid. In this regime, at low magnetic fields, this is not superconductivity in a strange metal. It is superconductivity appearing out of a Fermi liquid. And we see these behaviors both in the sample resistance and in the contact resistance, so both in green and orange. So that's telling us that the contact resistance is also probing the sample and contributing to this so-called contact resistance. That's why I put inverted commas around contact. So that's denoted here in this cartoon. Okay, so now what about superconducting onset then? We're still in zero magnetic field. So orange, let's look at green first, okay. Green is the sample, the real part of the sample impedance. That shows a clear superconducting transition at 6 millikelvin. And as we're measuring resistance with nano-ohm resolutions, I haven't shown this on a logarithmic scale, but the resistance in this regime is at the nano-ohm level. So it's truly a superconductor. So that defines a transition temperature, which I'm going to call T sub S. That's the transition temperature in the sample. But if you look at the contact resistance, that shows a sharp feature at a much higher temperature, TB. And I call it TB because it's reminiscent then of this feature in the diamagnetism that was seen in very low magnetic fields in the Schubert experiment, and happens at more or less the same sort of temperature. And then there is another transition at TA, which you can't see in the resistance. Maybe I better explain that first. So at TA, then let's take a blow up of this. The real part of the sample resistance is essentially zero. But if you look at the imaginary part as a function of frequency, you can see there's a step in the imaginary step-like feature over a reasonably narrow temperature range in the imaginary part. So this step is proportional to frequency, so you can infer then that the effective sample inductance is going down as you cross this TA feature. So what we're seeing then is a transition between two distinct superconducting transport regimes. This transition is happening at 1.5 millikelvin. And so we identify that then with the transition that's seen in the diamagnetism, which is labeled at 2 millikelvin, but there are issues with temperature measurement, I think, here. But that is essentially the same transition. And as I said at the beginning, in zero magnetic field coincides with the heat capacity anomaly. Here's the data on persistent currents. I won't go into that, but it shows that the persistent currents appear pretty close to the sample superconducting transition, and you even have in this data evidence of quantization to a level of about 20% of the flux in the input circuit. So definitive confirmation of superconductivity, which which really wasn't there apart from the diamagnetism signature in the Schubert experiment. So then you might ask the question, since this isn't helium-3, we have to worry about sample variations. So we study a whole bunch of samples, and all of these various transition temperatures that I've identified. Then the L temperature at 70 or so millikelvin, this TB feature in the contact resistance, the TS feature in the sample resistance, the TA feature in the sample inductance are all robust across these samples. What is not robust is the ability to observe persistent currents, because that requires a continuous superconducting loop. So if something nasty happens in the contact region, you can easily, one weak point can totally kill the ability to observe persistent currents. So now what we want to do is we want to explore the phase diagram in the with magnetic field. So we're looking here at the real part of the sample impedance as a function of temperature in different magnetic fields. So what you see is the following features. There's a shift down in the sample transition temperature. There's also a shift down in this feature TB, which is seen only in the contact resistance. There's a transition between different superconducting transport regimes at 1.5 millikelvin in the sample that doesn't shift hardly at all with magnetic field. And then there's a re-entrance of the normal state. So that leads one to construct the following phase diagrams with these, so magnetic field perpendicular to the z-axis as a function of temperature. This is the line of persistent, which we see persistent currents. So let's take you through that then. Here's the shift in the sample transition temperature. There's the shift in the contact resistance transition, the transition between different transport regimes at 1.5 millikelvin doesn't shift. Here is the labeling is interesting, but roughly speaking, here is the re-entrance of the normal state, and here is the signature of the onset of persistent currents, which you see has a quadratic type field dependence, and then hits the TA line, and you see that kink then also confirms the existence of a change in the superconductivity at this characteristic temperature TA. Now we do the same thing for fields parallel to the z-axis, and you see similar signatures qualitatively, at least, in the shift in all of these various transitions. You also see re-entrance of the normal state, and so that's summarized then on this phase diagram. So what we better do is compare the two field orientations. So if we look at the initial slope of the depression of the superconducting transition temperature, then using conventional theory for that slope, we can infer an upper critical field of about 30 millitesla, and that gives you a coherence length of order 100 nanometers, which is relatively isotropic. And that large value of the coherence length, despite the fact that we're in a heavy fermion system, so the Fermi velocity is relatively low, of course the transition is happening at a low temperature, so the gap is small, and so that combination gives you then can give you this relatively large coherence length. So now if you work out using the known G factors, what is the Pauli limiting field for this field orientation? It's 6 millitesla, and for this orientation it's 130 millitesla. So we're vastly exceeding the Pauli limiting field for both field orientations. For technical reasons, this field orientation was only studied over a relatively limited range of magnetic fields. But what you can see for field applied along the z-axis is that it starts out with this conventional linear suppression. That's where we get the coherence length from. But then there's this curvature. So it's an unusual field dependence of the critical field, which is reminiscent of what's seen in uranium ditelluride. for temperatures greater than TA, we have we're not confident that we're dealing with a uniform system, that there are inhomogeneities. So we have to be very careful about the fact that, as is well known, the signatures of superconductivity in transport measurements are subject to inhomogeneity effects and can occur at much higher temperatures than thermodynamic signatures. In the extreme form, that's referred to as filamentary superconductivity. So we see these phases here, which exceed the Pauli limit, and here we have evidence indeed that the critical field exceeds the conventional value that you would extrapolate from this linear slope because of this unusual field dependence of the BT phase diagram. Anyway, this multiplicity of transport regimes also, and the behavior of the critical field all suggest spin triplet pairing. And, you know, maybe that's not so surprising because YRS has strong ferromagnetic spin fluctuations, which are competing with the antiferromagnetic spin fluctuations, and ferromagnetic spin fluctuations would definitely stabilize spin triplet. So then what about at temperatures less than TA? So this is over here. So we see re-entrance of the normal state for both field orientations. It happens at a much lower magnetic field, around 10 millitesla for field in the AB plane, whereas it's only kicking in at about 200 millitesla for fields along the C axis. And even then, actually, the resistance doesn't fully recover the normal state value. But that anisotropy in the re-entrance of the normal state is kind of understandable in terms of the anisotropy of the electronic G factor for those two orientations. And what is robust between these two field orientations is this phase that I'm going to call, this is local labeling, SC4. So the phase that you see as you cool below TA in zero magnetic field is seen in both field orientations and is relatively robust.
So just to,
yeah,
many phases here, but do I understand right that only phase 4 do you think you've got bulk superconductivity and the other ones are potentially filamentary?
There's a strong possibility that that's the case, yeah. Yeah.
Why would that make it much more robust than the other phases?
Because this phase appears below this anomaly, which indicates a transition in the electronic magnetism. It could indeed be promoted by the electronic state, by the electronic state. This is using the language that we have at this transition. We induce a spatially modulated electronic moment that I'm loosely referring to as spin density wave order. But what we're pointing out here, again, we saw it at the beginning, is that this is certainly in zero magnetic field, the transition in the superconducting state and in the electronic magnetic order is simultaneous, and that raises the possibility of intertwined order. So I wanted, what we were keen to do, this relates partly to the question, is to explore samples with field in the AB plane out towards the quantum critical field. Now, for one reason or another, the sample that we had was relatively thin and more subject to strain effects. So what this is showing you is and sorry for it, in fact it's so small, this is the zero field transition. So it's occurring initially at 11 millikelvin, and it's meandering down to zero over a wide temperature range, but it reaches zero at about 1.5 millikelvin. So here is a color plot of the sample resistance over field temperature phase space. So dark blue refers to well superconducting regime, and you can see this is the SC4 phase at temperatures below 1.5 millikelvin. It's present in this, even in this strain, in this strain sample in this bottom left-hand corner, low temperatures below 1.5 millikelvin and low magnetic fields. But what's interesting, so that's one thing. The other thing is that you can see, so yellow indicates normal state. So this is the re-entrance of the normal state. And then as we approach the quantum critical point, we see a reduction in the resistance that, and I had to use a thesaurus to find the right word, hopefully it's incipient superconductivity at a shifted quantum critical point. So in this particular set of measurements, the resistance is only dropping by about 20% from its normal state value, but it is dropping, and the color plot shows the systematics of how that's dropping. So there's something interesting happening in the vicinity of the quantum critical point. And if we measure it on a better quality sample, and maybe in a slightly different way, we could reveal something in that. So then we turned to the following. Since the coupling between the electronic magnetism and the nuclear moments is key to this 1.5 millikelvin transition, one could ask the question, what happens if you tune the nuclear magnetism by isotopic substitution? So at vast effort and expense, the Krellner group has grown samples which are better than 99% enriched with ytterbium 17174, which has no nuclear magnetism, and about the same degree of enrichment with 171, which has a spin 1/2, and not quite so good enrichment with 173, which turns out to have lanthanum impurities. These have been characterized by Manuel Brando, and you can see for 171 and 173, there's a pretty sharp Néel transition temperature picked up in the heat capacity at 70 millikelvin. So these are good quality samples from the point of view of the Néel transition, but also the RRR is pretty good. So let's look at the effect of that on the superconductivity. Well, first of all, in the left-hand panel, here you see the natural sample in black. There's the kink from linear to quadratic at the Néel transition. So we've looked at two samples of 174 enriched. This one here has a kink at more or less the same Néel transition, and this one has a kink at slightly higher Néel transition temperature, and that's indicative. We know that that's indicative of strain in the sample, whether the strain is and the shift is due to strain, and the broadening is due to a distribution of strain in the sample. Now, if we go to lower temperatures, this is the superconducting signature in the natural sample, and it also has remember this other signature at 1.5 millikelvin into this more robust state. And that signature into the more robust state is driven by the nuclear spins. And we see very, very weak effects in the 174 enriched samples, 2 174 rich samples. That you notice that the temperature dependence of the resistance isn't the same for these 2 nominally identical samples. But they definitely aren't showing a transition into a robust superconducting state at 1.5 millikelvin. So that sort of confirms this idea of the interplay between the change in electronic magnetism driven by nuclear magnetism coinciding with superconductivity at 1.5 millikelvin. And then here's 171. So now we have rather than having random magnetic nuclear spins all over the place in our sample, well, not all over the place, on ytterbium sites in our sample, what we have here is an ordered lattice of spin-1/2 ytterbium, and what you see is that there is so this is now the gold line. There is no signature of superconductivity, in fact, but there are kinks which indicates probably some kind of electro-nuclear transition at below 4 millikelvin. And Jan Knapp is actually using this thermodynamic model, which I described earlier. You can solve the problem of coupled spin-1/2s with electronic moments with that form of the free energy analytically, and it shows indeed a magnetic transition at a temperature on the order of 1 millikelvin. So the fact that there should be a magnetic transition is not surprising. There's an indication that we can see that in the resistivity, but there's no superconductivity. Then there's a bunch of other work on focused ion beam microstructures that, given the pressure on time, I will just whiz through. The initial sample was this long meander. It was somewhat strained because it was glued down with Sticast in those days, and it had a TN shifted to 120 millikelvin, but nevertheless it shows there's a pretty sharp transition at around 1.5 millikelvin, and the kink at the Néel transition is not that bad either. Because of this, if you remember, various signatures in the contact resistance and the sample resistance, where we believe that the contact resistance will be more sensitive to the resistivity along the C-axis. We were concerned to try and look at anisotropy of superconducting onset, but it's very difficult to disentangle that from the sample strain that exists also in these FIB structures. That's the take-home message from that. So even when Kent Shearer worked extremely hard to make a new FIB structure that was designed for strain relief, what you see is so it's a wire. I should have explained this. So here's an example of a wire. There's the C-axis, there's the A-axis, and there's current. We can probe different sections of this. So we can probe this bit here where the transport is along the C-axis, and then we can probe this bit here where the transport is along the A-axis. And what you see then is that the Néel temperature is in more or less the same place for both field directions, but there are some shifts between the two current directions for this is A axis and this is C axis, but then there's this rather ugly temperature dependence, which is indicative of residual strain that's probably inevitable in these FIB machined samples, because they're square cross section, they've got corners. It's probably very difficult to totally eliminate strain, but the message that comes out of that is that strain is important, and so we can turn that on its head and use the FIB geometry to apply strains that are larger than any residual strain in the sample, and use strain to tune the superconductivity in a controlled way. But even despite all of that, the feature of 1.5 millikelvin, the disappearance of resistance at that sort of temperature, seems to be a robust feature, not so sensitive to strain as the various other features. So here we might get into a discussion about possible spin triplet order parameters, and one candidate for this phase here, appearing at low magnetic fields, coincident with the onset of the spin density wave, was suggested by Seamus to Jan in his PhD viva. So it's a candidate for a pair density wave in which you have some ESP type state, which would naturally give you a modulated electronic order. Maybe I'll reserve this for possible discussion either within this session or beyond. So, oh yeah, I'm sorry, I forgot. So here's the proposal then for that this is a candidate for PDW order. What theory is there on the market? Well, so none of this data have been published, but they've been talked about. So the group that saw one earlier presentation then used that to as motivation, I think, to look at what the phase diagram in this system would be. And what this plot shows then is this is the essentially the relatively long wavelength reciprocal lattice vector of the dominant spin fluctuations in the system. So when this reciprocal lattice vector is relatively short, then that in their picture enhances px plus ipy chiral type superconductivity, and you can even get D wave if you have much shorter length scale dominance to the spin fluctuation spectrum. So this is a theory about how the nature of the spin fluctuations can have a strong impact on the ordering in this system. So you might ask the question, why I'm talking about this regime down here in low magnetic fields, is superconductivity in this material so elusive? So I thought it was very interesting when talking to Lonsrich, and this slide, this part of the slide here is from Lonsrich, that in considerations of spin fluctuation mediated pairing, what's down here in the bottom left-hand corner is nearly ferromagnetic 3D spin fluctuations. So it's those that really disfavor, that those are the worst type of spin fluctuations for creating a superconducting order. And maybe that's what we're fighting against in this material. And then who knows what's happening in the vicinity of the quantum critical point, but it certainly isn't fully superconducting, and nobody has seen that. So what does this, where does the sample inductance come from? So why does the complex electrical impedance of a superconductor have an inductive component? So one possible origin is kinetic inductance. That's the energy of the supercurrent. That's the energy expressed in the form of an inductance. And so you can write this in a relatively neat form. Then it depends on the London penetration depth times some geometrical factor. And that geometrical factor is the integral over the length of some channel of the inverse area of the channel. So you can consider 1D filaments or 2D filaments, and then they're going to give you then an upper bound on the kinetic inductance, which depends on some combination of the London penetration depth and the coherence length. And by the way, we know what this ratio is because we know more or less what the ratio of the upper critical field and the lower critical field is, and some geometrical factors. So that's something that actually needs to be explored more, but that's locally one favored explanation of what's going on. This coupled with inhomogeneity of the sample is accounting for a lot of stuff. Another possible origin then is, again, actually, this was pointed out in a conversation with Seamus when we saw this apparent transition at TA by another method, actually, several years ago. He said, well, for goodness sake, you need to measure the complex impedance, which is what we did. And the change in the vortex structure between one phase and another would be potentially reflected in that, because vortices contribute to vortex motion contributes to sample inductance. So here we're considering vortices that are pinned, so they are subject to some restoring force about their pinning site. Their motion is driven by the Lorentz force, or is it the Magnus force? And they're subject to some viscous relaxation process. And so the ratio of K over eta defines a characteristic frequency. This thing out the front is the DC flux flow resistivity that you would get if you apply sufficiently strong forces to depin the vortices. So there's this ancient paper in which this kind of stuff was seen in the real part and the imaginary part of the impedance in some normal metal, and I've forgotten what it is. But to note that if we're dealing with a spin triplet, then there's, or in general, an unconventional superconductor, then there's all sorts of action going on in terms of bound states that the vortex cause, which is going to influence the dynamics of vortices. And I'll show you a plot in a minute. And the other possibility is that the superconductivity is coupled to other magnetic degrees of freedom, intertwined in some way. And so the upshot of that would be some inductive like response. So the piece of experimental evidence here is that we need to tension this data with those three ideas, but I wanted to be upfront about what it is that we actually see is with magnetic field. This is fields applied along the z-axis. We see this huge variation in the sample inductance, and actually this has the sample inductance has different field dependencies for two sample orientations, and we don't really fully understand that. But I think since this is show and tell of experimental data, I want to show that. It could have a really boring explanation in terms of inhomogeneities in a sample with a spin triplet order parameter that's oriented in different ways throughout the sample. And that modifies then the path, and these different orientations have different critical fields, which means that the pathway for a supercurrent through the sample becomes more and more tenuous, and the more tenuous the pathway, the higher the inductance is going to, the effective kinetic inductance is going to be via this geometrical contribution to the kinetic inductance. So that could be going on. So anyway, I think it's 10 minutes before or 9 minutes before I'm due to stop. So I'll quickly take you through a summary. So what have we done? YrS is convincingly a superconductor with sub-nano-ohm resistance. It demonstrates persistent currents. We have compelling evidence for spin triplet pairing because of the multiple transport regimes and the nature of the critical field data. Under certain conditions, we see re-entrance of the normal state on cooling. That has to do with sample magnetism, at least in part, because it's anisotropic for the two field directions, and this material is magnetically anisotropic. In low magnetic fields, despite what anybody tells you, the superconductivity appears out of a normal Fermi liquid. We know that we have ferromagnetic and anti-ferromagnetic spin fluctuations in the system. So my guess is that they're the driver. We have a heat capacity signature at TA, in which we get a new phase with a spatially modulated electronic moment. We can tune that transition within plane field. And our simple thermodynamic model predicts that there is a quantum critical point at which this order is quenched, but we had to have measurements to confirm that. In low magnetic fields below that transition temperature, we see a new superconducting phase, SC4, which is identified with the diamagnetically screened phase seen by Schubert. It appears to be correlated and maybe even intertwined with this new electronic order that appears at TA in low fields, candidate for a pair density wave. Fact is that the superconductivity is very sensitive to strain. So we're worrying about inhomogeneous superconductivity at temperatures greater than TA within these multiple transport regimes. The frequency dependence of the sample electrical impedance needs further investigation, because that will help us model these various candidates for the origins of the sample inductance to do with inhomogeneous effects or vortices or some intrinsic behavior. And last but not least, we see incipient superconductivity at the quantum critical point for in-plane fields. This is surviving the critical fields that we're determining from the low field data. So does this have to do at all with superconductivity without quasi-particles? This is what we want to do next. So these are all the things to do, but you need an army of people to do it. We don't have an army of people. That's the problem. Unless you want to give me one. Mercenaries. That's what I need. Mercenaries.
Next question. The audience has been very quiet during this long talk, so now's the time.
There's probably evidence of the triplet that's coexisting with the spin density wave of the nuclei. So there's a re-entrance that comes back when that goes away.
What do you want to? You want to see the data, or
different transitions and which will coexist with that spin density wave?
Okay.
Yeah.
So let me see if I can find. So this phase is appearing in this. We'll take this data for this so this phase is appearing in the bottom left-hand corner. This vertical axis is actually in Gauss, so that's unfortunate. We see this magnetic transition up to here. Right, so you're seeing a magnetic transition at around 1.3 millikelvin, even at this magnetic field, where there is no superconductivity. But down here in low magnetic fields, up to 8 millitesla, you see the transition in the heat capacity and the transition in the superconductivity, and they coincide. And that's what the coincidence actually looks like. Now, on a better quality sample, we need to explore the alignment of the disappearance of the superconducting onset with the evolution of the heat capacity. But the physical nature of the system is very, am I getting the wrong way? Is very different in the as a function of magnetic field, right? So in zero magnetic field, you would just have, according to our simple piece of thermodynamics, the spin density wave order. But as you apply a magnetic field, you get this growth in the what we're calling the paramagnetic component parallel to the magnetic field, which is ultimately going to lead to the destruction of the spin density wave state. The destruction of that spin density wave state is happening at a higher magnetic field than the destruction of superconductivity. So you could be in a world where applying the magnetic field, inducing this in-plane component parallel to the magnet is just complicating the issue. And the cleanest system is this one that you're looking at now, where you have a very sharp peak in the heat capacity. You just have this antiferromagnetic action without anything else happening in the magnetism, and you have the superconductivity. So so this is probably the most fertile place to be thinking about the intertwining of the electronic order, and it just gets messed up as you go up in magnetic fields. That's how I think about it. Let's understand this feature, that's part one, and then how it all disappears is probably a more complicated story. That would be my sort of methodology there. Seamus.
So in the theories for the superconducting order parameter, do they have a plausible model for the Fermi surface from which they're beginning? Because at the beginning of your talk, you said that they somehow don't take cognizance of the Fermi surface.
Most of the time, so I'm a new entry into the study of this material. So that's the impression that I got, and the experts may, question that. Definitely in that paper from the Chinese group on the superconducting order, they actually calculated the Fermi surface.
That structure.
Yeah.
Okay.
Yeah.
Online. No, you've got a hand up. Did you have your volume up?
Do I have my volume up? I've no idea.
Julian, can you speak? Yes.
Hello? Hello?
Oh, my volume is not up.
Ah, yes. Thank you. I am quite far away. Thank you for the talk. It's too much information for the breakfast time here.
Just tell him that we can't hear yet.
I have some echo. Well, my question is quite simple. I missed the evaluation of the entropy in this.
I can't hear.
well, I repeat the question. I missed the evaluation of the entropy from this specific heat because what I can see in this figure, for example, there is a huge amount of entropy accumulated at low temperature, and this can give you as a reference concerning which is the role of the nuclear levels or nuclear degrees of freedom. Do you have evaluated this evolution of the entropy?
Yeah, thanks. So as I understood your question, there's a large entropy release at low temperatures, and indeed, as I tried to discuss earlier in the talk, all of the entropy that we're measuring in the system is the nuclear spin entropy of this roughly 15% of 171 and 15% of 173. It's all nuclear entropy.
Okay, yeah. So it's not you cannot distinguish
the,
it is involved into the superconductivity.
So the entropy.
Can you distinguish if these degrees of freedom are involved in the superconductivity?
Can you distinguish the degrees of freedom involved in the superconductivity?
So the question, I guess the question is related to the thing that Piers is interested in, is to what extent the nuclear degrees of freedom are entangled with the superconductivity.
Right.
All I can say is that we just developed using the principle of Occam's razor, I guess, and our ability to calculate anything as experimentalists. That's probably the most, they had equal importance, that's probably. We neglected all of that stuff and asked the question with the simplest possible picture, namely electronic spins which are just non-interacting and subject to the local hyperfine field from the electronic magnetism. What would you expect to see? And on the basis of that model, we can explain quite a lot of the data. I would say that the thing that isn't really explained is phenomenologically, we fit this sharp heat capacity anomaly to an ansatz for the order, for the electronic order, and that has an exponent. So we have no idea where that exponent comes from, but it's in that the microscopic details of what's going on in this system would reside. We have no microscopic calculation. Therefore, we can't comment on to what extent this or that or the other degrees of freedom are involved. What we have is an exponent. And what we need is a theorist to provide to do the microscopic calculation to account for that exponent. I think that's how I would see the methodology here from my perspective.
Can you give
Well,
a number for the super stiffness? We could imagine if it were BCS like, it would be the concentration of electrons times E squared over some m star. M star is the mass of the electrons. Can you compare quantitatively with that number? Is it much smaller than that number, around that number, bigger than that number?
Well, so the way that you measure the superfluid, I'm not going to answer your question, but I'm going to talk around it. The way that you measure that would be to measure the London penetration depth. The kinetic inductance is determined by the London penetration depth squared over times some geometric factors. This is the difficulty, and so it's separating those two things out. It could be the case that if you did a measurement on an FIB structure, which is a wire, so that the filamentaryness that you might have in a single crystal would be more under control. You could be able to separate out those two things and determine what the kinetic inductance actually was.
Okay, any last questions? A great morning. Let's thank John for his second talk. It was great. And we will resume. Well, it's going to be at 2:30. Did I get that right? Yeah, 2:30. Yeah. Okay.